So this is the last part that we have. We can compute the surface integral based on the definitions using the double integral and then multiply with the area or surface area, right? Okay. Now one more example here, and then we are going to finish off the last sections in the surface integral with what we call as the oriented surface. So let's say we have this surface that we have S1, S2, and S3. They are all surfaces. Okay, so S2 will be the projections on the XY plane. S1 is the surfaces on the sides. And then S3 will be the surface on the top, okay, if you could see it from the picture. And then we would like to know the surface integrations ZDS, where S is the S1, which is the cylinder x squared plus y squared equal 1, and half the bottom S2, x squared plus y squared less equal 1, okay, the projections, and the top will be the z equal 1 plus x. Now we could write here, because they are all in terms of, we can relate some of them with a polar, then perhaps we could convert this to polar. So let's say to make it polar, we could make it, for example, from the circle x squared plus y squared equal 1, we know that the radius is 1. So the x could be just cos theta, and then y will be sine theta, and z is still z, just to mention that it's only still the height of itself. And then the parameter, we can use theta and z. So theta, we can think theta from 0 to 2 pi. And then we have parameter z from z equals 0, so this is z equals 0 here, until z equals 1 plus x, or 1 plus cos theta. So we can also evaluate z from 0 to 1 plus x, or in this case 1 plus cosine theta. Okay. So we are going to take the parameter. So parameter is theta and z. Okay. So we can take the cross product for theta and z, or suppose that we can write r theta is negative sine theta I plus cosine theta j, and rz, so all 0 and only have one z, so this is zk, right? We can make this as a cross product, so let's cross this. So I, j, k, oh, is this not z? Sorry. We derive this, so this become 1. Okay. And then this will be cosine theta, right? And 0, 0, 0, 1. Remember that these two are partial, the first partial derivative. Okay, so we take the cross product. So we have cos theta I, and then minus sine j, and for the k will be 0, and then take the magnitude cosine squared theta plus sine squared theta will be equal to 1. So the result is the surface z ds is equal double integral for the region D, and then we take this dA, and from what we have we could write this is should have the z. So this is z dA with respect to area D. Now the area D, we could use this area D as the projections. So we could use this parameter for D. So we could take that circle from 0 to 2 pi, and then z is from 0 to 1 plus cos theta, and z dz d theta. And then this will be, we integrate the one inside here, it will be half z squared, and then plug in 1 plus cos theta. This will be half okay, and then we solve this will be half plus cos theta over 2, and then I need to make it here. So half multiply with 3 over 2 theta, and then it's the same cos, oh so sorry, it should be double angle, so plus 2 sine, and then plus 1 over 4 sine. Sine will be 0 because of 2 pi and 0, so we only have 3 pi multiplied by half, it's 3 over 2 pi. So basically the idea for the surface integral is you need to define your parameter. Usually we define in the examples previously, and how we prove that is through u and v. So u and v, that is I think one way to describe, and in this case what we describe here, we take the theta and z. So we are not fully converting the double integrals into the polar double integrals. So we only adding the theta from 0 to 2 pi, because what we want here is we want to make sure that the computations or the calculations will be about the surface, not the volume. If we take the theta and the radius, in the double integrals polar, if you remember in calculus 2, what we did is we are evaluating the volume, right? But here we want to make sure that our calculations is basically the area. So that's why the formula should be in terms of this cross and then dA. And dA basically we can get dA if you take back the what we have in previous examples. It will be the surface area for the integrations, okay, which defined by similar magnitude, basically like this one here. And if you remember that this is also in similar with the arc length, like 1 plus dy dx squared or dx dy squared, or in the surface area is 1 plus dy dt squared and dx dt squared, okay. Or partial, okay, partial x squared, partial y squared. That's the surface area. Let me just give you a little bit moment here. So this is what we have, okay? So this is actually the idea. But we can also, because basically this part is based on the cross product here, that we can also make out from the scratch, as long as we know the cross product. As long as we know the cross product, we can basically set up the cross product and set up the parameter. Okay? The previous example here, we set up parameter phi and theta. We set up this parameter based on the spherical coordinates. And then we can also have this. Okay, this is the surface area. Okay, so it's either this or using the cross product, because they're basically the same thing. The cross product magnitude value is basically the area of parallelogram in vectors. Okay, so this is basically the same area. So that's why we can also have this. So let me just maybe give you notes that this is the, we can also take the area of parallelogram in vector. Okay, but this is not yet completed. We only have this is for S1, okay, because S is having the S2 and also S3, right? So we are going to see, can we get the other part as well? So I think I need to make this a little bit out here. Okay, let me write here for S2. This is for S1. This is for S1. And for S2, because S2 is on the z equals 0, right? It's on the z equals 0, so the surface integrals on S2 of z ds, because z is equal to 0, then this will be 0, okay? Because this will be equal to 0. Now, for S3, this is going to be the surface that on the top we have 1 plus x. Now we are using the other structure for the surface. So let's say this is ZDS. And we are using this 1 plus x. So this is 1 plus x. And then the area, or the supposed to be the parallelogram, will be based on the surface area that we have learned before. So this will be the partial dz dx and dz dy. And then dA. And remember now for this S3, we can convert the double integrations into the polar nicely, because it means that we take this as our z, and then this area will be our region for integrations. So we can take this, and from the x squared plus y squared equal 1, we know theta is from 0 to 2 pi, and r will be from 0 to 1. So this will be 0, 2 pi, 0, 1. And this will be 1 plus r cosine theta. So 1 plus 1, and the rest will be 0. And dA will be the r, dr, d theta. I will factor out the square root of 2. D theta will be here, 0, 1. Oh, I think we cannot do this. Let me. So let me take this 1 plus r, multiply with r. So this will be r plus r squared cosine theta, dr d theta. So take the integration with respect to r. This will be half r squared plus 1 over 3 r cubed. And then take the 1 to 0. So this will be half plus 1 over 3 cosine theta, and then d theta. And then one more, we have half theta plus sine theta over 3. From 0 to 2 pi, and sine will be 0, so this will be pi, right? So square root of 2 pi. So the final result will be the total expressions for the S1, S2, and S3. So this doubles integral the surface with respect to S. This will be surface S1 plus surface S2 plus surface S3. Surface S2 is 0, so we just add this 3 over 2 pi plus square root of 2 pi, or pi 3 over 2 plus square root of 2. This will be the final result. So the surface could be determined by the whole part of the surface in the parameter. like this one here, we have in all part of the surface. So you have the surface on the top, surface on the body, and a surface on the ground, and then the surface integrations for this part, because it's defined through whole surfaces. Then we need to add each one of them. Okay. I think from this example, you could take some key points that you can also use that as a like a requirements or conditions. Just look at this surface. Okay? When you have the surface, like for example, the surface functions like in the calculus 2, which is this one. If you have this f, suppose it's f x y z or f x y, then the surface area, we can use the square root 1 plus the partial x partial y, 1 plus partial x squared partial y squared, and then we can compute. Okay, so that is if we have this. So if we have the surface that is on the circular part in the cylinder, then this one we need to create the vectors, which is we are going to build up the new parameter. Okay. In the proof or in the introduction, we build the parameter with u and v, but basically we are going to take that into our R and then partially derive R and then get the area of parallelogram. Okay. And I think that is what is likely to happen in more examples to come. And later, maybe if we have time, we can have a practice of that. Okay, so I think that is some notes, and perhaps it will also can be used for most of the cases. Okay. Now, aside from this computations and the surface integrals, technically, there is one thing that we call the orientations, or we call the oriented surface. Okay. Like as I mentioned at the beginning, that the surface, if we have like a sheet of layer, it could be oriented towards the top or towards bottom. So we could have at least two sides, right? But before we go for the orientations, if we look at this, like suppose that this is like a tape, and then you want to circle the tape, but you twist one sections, and if you imagine that you have the arrow from the inside, and the arrow will be only one side directions, okay? And they will be the same because of this twist. You could do the same thing if you maybe making the directions outward to outside here. This will also turns out that it's only one side. So it's either that or that. There's only one side. So this is what we call the Mobius strip. And basically, the one who found his name is Mobius, August Mobius. So this is the Mobius strip. So it what's the idea here? It has only one side one side orientation. Okay. Okay, this is just exceptions. Okay. Now, what we are going to focus more in this course is we are going to consider two sides. Okay, two sides. This two. Okay. Like imagine that you have the normal vectors for every part in the point in the surface, and you can have the normal vectors going out like this, or you can have the normal vectors going inside. Because we can do this, right? Both of them we consider as a normal vectors. Right? Because at every point, the cross product will result in the normal. Okay, so we can have this what we call the oriented surface. So for any orientable surface, there are only two possible orientations. Okay? And then for supposed to be, let's say, for a surface, we name Z, let's say G, X, Y. We can use the equation the unit normal, so then unit normal vector from the equation that we built, I think, at the early introduction of the surface integrals, which is this, the Rx cross Ry okay. From there, we can make this unit normal vector n, and practically we can write down this as the Ru cross Rv divided the magnitude. Okay, it's its magnitude. And for example, in the previous example that we found the sphere, let me just copy this, that we have the sphere here. Okay, suppose that this is having the radius A, okay, suppose the radius A, that the magnitude will be A squared sine. Okay, so in the sphere we can remember, then we can write the n also using this unit normal vector. So for sphere, where the r is based on the phi and theta, we can take this n equal r phi cross r theta divided by its magnitude. And since this, I will write the results. Okay, the same with the previous one, but the radius is we call the radius A. Maybe let me add here, just to take notes, with radius equal A. So sine phi cosine theta I plus sine phi sine theta j plus cosine phi k, and this will be equal to this is the r, okay, So we can write this as 1 over a r phi theta, because the magnitude value is a squared sine phi, and then we can basically divide all with this one, and the r phi cross r theta will result in the a sine, basically the same thing with a, and then we divide with a squared, it becomes 1 over a. Okay. Okay, just an example. Okay, just really quick example. And then we call the one that has outward orientations, we call the positive orientations. The one that has the inward orientation, we call this as a negative. So for a closed surface, we can make up this definitions for, or the terms. So this is for closed surface. Because basically, if you have these two conditions, it means that in the sphere, the r theta cross r phi, and if we switch the order, it will be the negative part of it. Okay, now these orientations, we are going to use that in observation of what we call as a flux. The flux is the surface integrals on the vector field. So you can imagine we have a surface and we have a vector field. The flux is how much this flux goes into the surface. I think the most reasonable way to think is by thinking for example, like the flux in the magnetic flux. I think easy to follow that, because we have the flux in the magnetic field, and then we put some layer on top of that, and we can see that the flux, the magnetic field, will go through this layer. Okay. Now let's get into that. Just a moment here. Okay, so suppose that imagine we have the vector fields, this red directions, red arrow, and then we have S, and this S is a surface we call oriented surface with normal vector n. So suppose S is oriented surface with unit normal vector n. And then we have a supposed to let's say fluid with density. So density, we have density function, which is rho, and velocity field, which is v, and then basically this density and velocity will make it into a vector field. So the vector field is the rate of the flow per unit area. And then if we slice the surface and makes into this Sij with with the n, and it has a particular vector fields. And we can also approximate, that this Sij here, on this one here, we can approximately that this is going to be nearly planar. And again, this is approximations because we slice the surface very, very small. And if we sum of all these quantities and taking the limit, so basically we take all this based on the surface integrals, vector field dot the n and then the s. We could, this is x, y, z, and then this is the velocity, and then dot the n and then the s. If you write that the f is rho v, we can turn this interpretations becomes the surface integrals of f dot n ds. And this form will be, I think you can see a lot of phenomenon in physics. So we call this the flux integrals. Flux integral f over some surface S. Maybe just notes here why this can be written as dots. So because it is nearly planar, then the mass per unit crossing Sij in direction n is approximately rho v dot n a, and we can use this to get into the definitions. So the definitions, if f is a vector field defined on some surface oriented surface S with unit normal vector n, the surface integral of f over S is surface integral f dot ds will be equal to surface integral f dot n ds. So you need also to distinguish that this S and this S is different. What does that mean? This S here, this is what we call the oriented surface. Either the orientation is going positive or negative if it's on the closed surface. But what does it mean is this is an oriented surface, and how it would be determined, the oriented surface, by the normal vector. So that's why we can separate, or we can break down this oriented surface becomes this NDS. And these integrations will be the flux. So the definition of the flux of F across the surface S. And again, from here, we could define into different, for example, if it is on the vector function RUV, for example, so if S is given by, let me write by RUV, then and we can take this as RU cross RV and then divide by the magnitude value. So we can exchange the magnitude, and then this would be so this is RU cross RV. This is RU cross RV multitude, and then the S, and then this will be equal. We are going to change it to the region D, and F will be based on the vector function UV. So dot RU cross RV and the S will be practically the same with the previous equations. And then this is dA. So dA will be dependent on the what is the region. And then this magnitude will cancel, right? This will cancel. So we can write the F dot ds as F dot RU cross RV. So the orientations for the N will be based on the cross product, okay? And if you compare the similarity with the line integrals, when we define the line integrals of a vector field, we have the, maybe it's also easier for you to remember that this is perhaps very similar to what we have in the line integral f dot dr, and this will be based on the f r of t dot r prime t dt. Okay, but the difference, because we are dealing with the 3-dimension in surface, and then we need to know what will be the orientations, and we need to dot the orientation, which is the normal vector that is dependent on the cross product of this partial r with respect to u and v. Otherwise, this is very similar. Okay, we can continue. Okay, so let's continue. So here is the example for finding the flux, so determining the flux. So here we have the sphere, and again, because we are going to have many examples and problems related to sphere, just to make sure that we are understand how to make the parametric representation of sphere. Let's say we are taking for sphere our parametric representation will be basically we are using two variables phi and theta, and this will be sine phi cos theta I plus sine phi sine theta for y-axis and plus the cosine phi k. So this is the R. So from this R we could find the cross, or we could find the partial for each one of them. So we have cosine phi cosine theta I plus this will be cosine phi sine theta j, and then this will be 0. Oh, this is not 0. This is sine negative sine phi k. And then the r theta will be negative and then this will be plus and this will be 0 practically. And then we take the cross. I think we have done this in the previous example, so I will just write the result. Cross this value, resulting sine okay, that's the cross. And then we have the vector field as mentioned in the questions, and yeah, basically we can use the vector field in terms of, so we put all the R inside the vector field and then dot the cross product. Okay. So then maybe let me write again the f x y z. This will be z I plus y j plus x k. So basically we are taking the R inside this equations. So all the R, which is sine phi cosine theta I plus blah blah blah, we are going to put inside and then dot the cross. Okay, dot the cross. And basically you can check whether this is correct or no, but we put the R inside F, so this will be, and then take the dot product, so this will be cosine phi sine squared phi cosine theta plus sine cube sine squared is quite long, so let me just write the results. Sine squared pi cos phi cosine theta. So sine phi, sine theta, let me check just for a moment. Dot the, okay. Yeah, should be correct. Should be correct. Okay. I just checked these one axis and it's okay. Okay, now by taking the surface integrals, f dot ds, this is equal to f dot the r. Right? Basically, this is these equations here. Okay. Cross the r theta dA, and we can take the d as the circle or the sphere. Okay, now we take d, take into sphere parameter, which is the sphere parameter will be phi and theta. So phi will be based on 0 to pi, and theta will be, okay, so the phi is the, if we draw theta is on the xy plane, this is the theta. The phi is on the z, this one. Okay, so that's why it has just 0 to pi. And then plug in the results. So we can, well, basically this is, we can add this too. This is sine squared phi, right? I think I will add this too. So 2 cosine phi sine squared phi cosine theta plus sine cube. Okay. So f we could put inside. And this will be d phi d theta. And I think we can make it becomes separate this two equations with double integrals. So the first one will be, we can write and this is the second one. Okay. And then based on the angle variable, we can separate by taking the Fubini theorem, if you remember. So we can take this for theta, so cos theta, d theta, and 0 pi, and maybe factor out 2. Okay. Take the same way. Yes.
Sine cube plus sin cube phi sama sin cube theta itu kayaknya sin kuadrat ya.
Sine cube, sine cube.
Ya pernah
Wait. Oh, right. Why it's becoming cube? Should be square. Sorry. Okay, this will be sine squared theta d theta. Okay. Now before we continue, we can see that this cosine, if we integrate, it will be sine, right? It will be sine, and then the integrations will be from 0 to 2 pi. Sine will be 0, right? So the whole thing will be 0, right? Okay. So we can focus only for the right part, which we can implies that this sine cube and the sine squared, this will result the same with the previous example, or if we have, I think we have example, right? The first example that we found at the early introduction of surface integrals. So this is going to be very similar. So this will be 4/3 pi. I think, let me check. This one. Okay. So that will be very similar. Or perhaps you can check through calculators if you want. Okay. Now this vector field in this example, we could describe this as a velocity field with density 1. And then this 4/3 pi is representing the rate. Okay, so this is a rate of flow through unit sphere. And again, this is in terms of, if we could, perhaps it's not in XY graph. It's on the parameter sphere parameter, right? But we can also think if we have a surface that has perhaps a function of two variables, surface functions, we could write differently for these equations here. So we could write, maybe let me just add here, make it this on the left. So we could write that. We could write in for z equal of g xy. So if we have this is a surface, and we can use x, y as parameters. So then the f dot rx cross ry, which is partial with respect to y and x, this will be basically, the f will be, let me introduce to pi plus qj plus rk. This is very similar to what we have in the previous theorem. And then dot, this will be, negative dodo xg I negative dodo y j plus k. So we may write the formula for the surface integral of f dot ds. We can write as this is. So we take the dot, and then this will be double integrations negative p negative q dou g dou y, and then plus r dA. So this could be true as well for xy as parameter. This assume positive orientation. So this assume positive orientations. Remember, orientations mean the normal vectors will be coming outward. Okay? If you are perhaps you have the vector fields and it gives you the condition that is negative, you can multiply with negative. Okay? You can multiply with negative. So if it is negative, then multiply with -1. And I think compared to what we have in the parametric surfaces, when we have the another axis, another parameter, if we just focus on the xy, I think it's technically a lot easier than, or a lot of technically easier, yeah, a lot easier. Because we need just to find the partial for x and y from our surface functions, and then multiply with the p and then just solve the integrations, define your region D, and then define your dA, could be dx dy, could be dy dx. Or it could be perhaps polar. So let me give you example so that you can have a good idea for what we have here. So suppose that we have a vector fields. We have vector fields, and then S is the boundary of the solid region E, which is below the paraboloid Z, and then the plane Z equals 0. And remember that since the plane Z is equal 0, then we could know that the S2, before we see the S1, the S2 will be 0. And then how do we know the orientations from this part here? And then for the surface that is supposed to have like this layer, the orientation goes down. But by default, we could sense this as a negative orientation assumption. I think I forgot to mention at the beginning. So assuming this, but although this is negative orientations, because the S2 is on the plane Z equals 0, and then when we plug into the f.ds later, we could see that it will give you 0 as well. Okay, but anyway, let's start off with the S1. Okay, start with the S1. So for S1, it means that we are going to focus on the paraboloid Z. And then from the F, we could break down PQR value. So this is P, this is Q, this is R. And we know Z is equal 1 minus x squared minus y squared paraboloid. We can substitute for this Z. Okay. Maybe this is confusing, maybe later we can. Maybe we could just assume from the picture this is positive orientation. I have. Okay. Okay, that's for S1, and then we could find the dou G dou X. And suppose this is the Z. Okay, so suppose that the Z, suppose that Z is gxy is 1 minus x squared minus y squared. Dou G dou X is negative 2x, dou G dou Y is negative 2y. So the double integral or surface integral for S1 f dot ds okay. So it's negative p is y, so negative y, dou G dou X is negative 2x, so it's become positive. So let's write here 2xy minus x minus 2y, so plus 2xy. R is z is 1 minus x squared plus 1 minus x squared minus y squared, and then the a. So let's simplify this. This will be 1 plus 4xy minus x squared minus y squared, and dA. Now D will be the region on the bottom part, which based on the double integrations we could convert to polar. Okay. So at z equals 0, then the x squared plus y squared is equal 1. So the circle will be having a radius 1, and the theta will be full circle from 0 to 2 pi. So we can use this as a conversion. So 1 plus 4, x will be r cosine theta, y will be r sine theta. This will be r squared cosine theta sine theta. Minus this x squared minus y squared will be minus r squared. Multiply with, don't forget to write r dr d theta. Okay, multiply first. This is r. Minus r cubed plus 4r cubed we can evaluate first. And then plug in 0 and 1. So we have half minus 1 over 4 is 1 over 4 plus cosine theta sine theta d theta. The cosine theta sine theta, we can get the sine 2 theta over 2, right? And then if we integrate sine, we will get negative cosine. But because we have 0 to 2 pi, this will resulting 0, right? This will be resulting 0, okay? So we have only 1 over 4, which we can multiply with 2 pi, becomes pi over 2. Okay, this is for S1. Now for S2, I think I make a mistake before. I said that this is negative. It's not the case. The case is, since it is downward, let me write here. So for S2, so it's oriented downward. So unit normal vector n is negative k. And make the same conclusions here. So negative k will be, if we dot f will be having y, x, z for each one of x's. So if we dot, this will be resulting in only z, right? So this will be negative z dA. And since z is equal 0 for the plane, so we know that this will be 0. So the total of the surface integrals this will be equal to pi over 2. And the rest, we only we still have at least one section So I put the exercises in between, like for example here, we have the surface integrals exercise, and the previous part we have the green theorem, the curl, and divergence. You could also check exercise. I put in between the sections in the notes. I will upload the notes later. You could check the exercise and the practice. We still have one more, at least one more theory. It should be two, but I think we only have maybe not much time left, so maybe adding one more theory, which is we call the Stokes theorem. And hopefully if I have time to give you more exercise, I will prepare and maybe give you just the additional videos. So our final exam is June 7, right? Okay. Okay, to end this course today, I would like just to give you a little bit introduction of the Stokes theorem. So what is the Stokes theorem? It's actually a green theorem, but in 3 dimensions. Okay. So yeah, this is all the exercise. I hope you can check that out. Okay, the Stokes theorem is basically, we call this as a higher version of the green theorem. In green theorem, we relate that we have the double integrals and double integral over d relates to line integral. Line integral on the plane boundary curve. So the Stokes theorem, it will basically relates the surface integral to a line integral. The difference will be the boundary, because in green theorem we are only projecting from the top side of the 3 dimension, but in Stokes theorem we could imagine this as you have a surface, and then you can make a boundary around the surface. Suppose that we have a surface with a normal vector n, so this is surface with normal vector n, and then we can have orientations that is going outward, and then because it is positive, so because this is positive, and basically most of the assumptions for the either Stokes or the previous surface integral, the positive will be the by default. Okay, we can assume that is positive, unless maybe it shows you different conditions. So this is positive orientations, and then because this is positive, then it means we move around C in positive direction. And remember, positive direction means counterclockwise. So it will be positive means counterclockwise. Now, if we flip this, and if we see from the top, then it will be the green here. Then we have the counterclockwise positive rotation, right? And then we can relate the line integral with this curve with the double integral over some d region, which is on this side. Now we can relate these Stokes, but maybe let me just give you the definition first, okay, before some proving. So let S be a oriented piecewise smooth surface that is bounded by simple closed piecewise smooth boundary curve. But basically, we have a closed curve C smooth with positive orientations, and then F is a vector field that goes through the surface, and then the component of the vector field need to be assumptions will be partially derivable on the open region that contains the S. Okay? And then we can write the line integral of this F dot dr will be equal to surface integrals of the curl F dot ds. Okay? So this is, I think, introduction for this, the Stokes theorem. That will combine or connect the line integral with the boundary C with the surface integral for the surface S. Okay. We are going to see more of this on the Monday class, but I think if we could finish the Stokes on Monday and then have some exercise for the next week Friday, we could have either the last part is actually we have what we call the divergence theorem, but if I give you that, maybe too much content. Well, let me think about it. If not, then perhaps we will have the exercise, practice and exercise. Okay, I think that will be for today's lecture.